This video is about Millikan's oil drop experiment to determine the charge on an electron. I'll let you read this background information about Robert Millikan, who was a very interesting gentleman. One of the most famous experimental physicists of the last century. Millikan's apparatus is really quite simple. You should be able to draw it on the diagram of it on the left. And the easiest way to learn what the experiment involved is to watch a quick little video, which is what I'm going to play now.
British physicist J.J. Thomson had measured the ratio of electrical charge to the mass of an electron using a cathode ray tube in 1897. Later, R.A. Millikan looked to determine the charge on the electrons. The famous method that he devised between 1906 and 1914 to measure the charge E of an electron is known as the Millikan's oil drop experiment. Using this method, he calculated that the charge on an electron was about 1.6 times 10 power negative 19 coulombs. In the Millikan's oil drop method, an atomizer produces oil droplets in the form of mist, which are sent through a plate of electrical condenser. There are different forces which act on the oil drop, including gravitational, electrostatic force due to electric field, and viscous drag force. The rate at which these drops fall were measured by observing them through a micrometer eyepiece of a telescope. X-rays were passed through the chamber to ionize the air inside. On colliding with gaseous ions, these oil droplets acquire charge. The rate at which these droplets fall can be controlled by changing the strength of applied voltage to the plate. With this experiment, he observed that the magnitude of electrical charge Q on the droplets is always a multiple of electrical charge E.
Now, let's look at this in a little more detail. Millikan and Fletcher spray a fine mist of droplets into this upper chamber. Now, there are two methods for charging the droplets. Sometimes the droplets receive a charge as they're sprayed out, just by friction with the nozzle of the spray piece. Alternatively, they can be given a charge by passing X-rays through the chamber. When they fall into the bottom chamber, they can be exposed to an electric field if it's turned on in the bottom chamber. Let's look at this electric field. The electric field is produced by two horizontal metal plates with a small hole which allows the oil droplets to fall in between the plates. And by applying a potential difference between the plates, then we can generate an electric field between them. You can calculate the strength of the electric field if you know the distance between the plates. A quick question for you is, what's the relevant formula for calculating the strength of the electric field between those two plates? It is on your data sheet. This slide is advanced. Millikan actually measured the velocity of the oil droplets. The experiment as described in your textbooks and in videos is really a simplified version of his experiments. But I think it's worth knowing that the real experiment involved measuring how quickly these oil droplets fell when there was no electric field, and then repeating the same measurements when the electric field was turned on and the oil droplets started to rise. It's much easier to do that than to try to perfectly set the voltage, the potential difference between the plates, so that the oil droplets are stationary. But the maths is really quite complicated. Now, you can ignore anything in your textbook that says that he stepped up the voltage. He didn't. You can actually read his paper. It's freely available online. And it's complicated, but it's pretty obvious that in his experiments he kept the voltage pretty much the same with each oil droplet. Now, from now on, we're going to look at the simplified version of his experiment. You'll see what I mean. So, we could work out the charge on an oil droplet by using this simple idea. We can adjust the potential difference between the plates until the oil droplet remains perfectly steady, just hovering in midair. That allows us to balance these two forces. It means that the electric force acting on the oil drop must be perfectly balanced by the weight force. So if I have an oil droplet, then there are two forces acting on it, and they must be perfectly balanced. Our weight force is balanced by our electric force. This wasn't Millikan's method, but it's a simplification and it lets you understand most of the important physics concepts involved. So, if we know the mass of the oil droplets, and if the oil droplets are in equilibrium, they're just hovering there with the forces equal, then the force on the oil droplets due to the electric field can be equated to the force of gravity. And if you substitute into this equation, you should arrive at this. We'll do this in the classroom, but I'll just point you to the formulae on your data sheet that you'll need. You need to know that the force on a charged particle equals the size of the charge times the electric field strength. You need to know that you can calculate the electric field strength using the potential difference between the two plates and the distance, and you also need a formula for weight, which of course you know is mass times the gravitational field strength. So you should now be able to show that the charge on the oil droplets is given by that equation. So Millikan made measurements on many, many oil droplets. And as you'd expect, each oil droplet picked up a different amount of charge from the air. Sometimes the oil droplets might have picked up, say, 500 electrons. Sometimes the oil droplets might have picked up only 10 electrons. But Millikan found that the charges picked up by the oil droplets were all found to be multiples of a single number. And that number is, of course, the fundamental electric charge, the charge on an electron. So the experiment confirmed that charge is quantized. The charge on any object is equal to the number of electrons that it's lost or gained. So charge isn't continuous. It can only exist in multiples of a base unit, which is of course a charge on an electron. Millikan measured the charge on an electron extremely accurately, 1.6 times 10 to the minus 19 coulombs, which is exactly the same value that you use in your calculations. Now, before you go into a simulation, I really recommend watching this video by Tyler DeWitt. It goes for 12 minutes, but it explains these concepts really well. Following that, you should do this simulation. It really reproduces the simplified experiment very, very well. That's it. We'll do sample problems and solve any questions that you have during our lesson.